have been getting the notes. And like I've been repeating throughout the course, a lot of these, the topics that we are covering are proper in-depth coverage would require weeks, if not months, right? So we are kind of scratching the surface, leaving it there. So that can be quite annoying for some people. But the point is to show you the proper direction and where to look for information, right? And if you need further guidance on any of these topics, do write to us. We'll be happy to help you with more literature, more papers, whatever other information that we can guide you with. Now, the last session, basically, this is aimed at bringing everything home now. So we've started with rheology, then we understood what is rheology, how do you measure the flow property of a suspension or a fluid. Now, and then when you go to concrete, what is the level of discretization that we can go with? Where do you draw the line? What is the fluid medium? What is the solid medium? That's entirely up to you. So, and at that level of discretization, then, what is the role of rheology of the fluid? What is the role of the solids that are making up the solid fraction of the composite? Right? And what do we mean by composite? Concrete is a composite. It's not a single material. It's multiple materials, right? So then there are the fresh properties and the hardened properties, right? Now, both are covered even in conventional mixed design, because we have to design a concrete, even for a regular concrete mix, for what we call slump. Basically becomes our measure of, some measure of flow. When we say it has a certain slump, we immediately picture, okay, this is concrete that's going to flow more, or it is going to be very stiff, right? That is the association we make. Is still something that is an evolving field, and probably you cannot directly use it, but every indication is that, if I have a certain slump property, a certain drop table flow property, I know what I'll expect when it comes to rest after I'm done pumping, and how quickly or easily will it fill the form, and all these things come up for regular concrete. Now extend that to the case of printed concrete with its own requirements, which are pumping, then it has its extruded, so extrusion, and then shape retention followed by buildability. And all of these are related to definite thixotropic, definite properties of the fluid phase, ultimately of the suspension, right? So what I want to do here is now getting into the hardened properties. So what we are looking at is connecting the material properties with the structural performance of a 3D printed structure. Narayana has already done it. Some part of it will be repetition. But this whole exercise, we take it for granted, right? When we design a reinforced concrete structure, say you follow IS 456, if you actually pay attention to IS 456, the first few chapters of 456 deal with concrete as a material before you get into design provisions. The design provisions are from chapter 3 onwards. Chapter 1 and chapter 2 of IS 456 deal with the material, its flow, its strength, quality, and all of these things, right? Now, we take it for granted that if I know the compressive strength, I can design a concrete structure. The entire science behind it has already been developed. Now, that has to be done for printed concrete because of its own peculiarities. We have to deal with it separately, right? Now, what are the challenges that we are talking about when you talk about 3D-CP? So we have continuity issues between layers. So if I have multiple layers, how continuous is it? It's not. It's actually, if you think about it, it's not a continuum there. There is a gap that will come up there because these are physically two different filaments, right? Now the question is, how then do I use whatever I get about the interface in designing a structure? How does it impact the overall composite behavior of a printed assembly? This is what I would call a printed assembly. If I scale it up, any printed structure is nothing but a printed assembly. So then the question is, if I do a smaller printed assembly, get some properties from there, how can I port it to the case of a larger structure? Then there are, of course, performance challenges, that is material property determination. When you have anisotropy, that is, if I test the material in different directions, I'll get different properties. Right? Which property do I report? When we talk about concrete, there's only one value that we report, that is the compressive strength. And supposedly that one value is the same no matter which direction you test, supposedly. Right? That doesn't happen here. Then how do I link the material properties to the structural behavior? Great, I've done this small scale laboratory specimen. Now I've tested it. How do I then go ahead and build with it or construct with it? So you've seen the reasons for the anisotropy. I think yesterday, the second half, and today the lecture was all about anisotropy. Why do we have this anisotropy? Two reasons. If I look at a filament itself as it is being extruded, because the shear stress distribution is not uniform across the cross section of a nozzle or across the cross section of a pipe, what happens is that you get shear induced movement of particles. Particle distribution doesn't remain uniform, and there's a tendency for paste to migrate to the surface. You saw that in the form of the skin that was showed in yesterday's lecture. So what happens there then? There is a non-uniform distribution of particles across the thickness of a single filament. So even that is not uniform. It's not homogeneous, as we call it. So that will have an impact on the properties. The other thing is that we have a layered composite. Basically, it's made up of multiple layers, and automatically there's a question of anisotropy, because now at every one of these gaps that we have, it's basically physically a gap. That how well it closes depends upon the material itself, right? So you deposited one layer, then the second layer comes and sits on it. So now when you're depositing two layers, suppose the two layers are very stiff, what will happen? The first layer comes up, and if you look at the shape that is at the surface, it may not be perfectly flat. It will have small undulations and all these things. That has to do with the aggregate. Now the next layer comes and it's also very stiff. What will happen? Those gaps will not close properly. And I'm not doing anything physically like vibrating it or pressing it, right? So what has to happen? Those gaps have to close naturally, right? So, but there'll be some gaps, and therefore what happens then? You basically start getting higher porosity at the interface, and you saw that, a consequence of that. Now the question is, if I was to say apply a shear force here, right, how does that shear force transfer take place across these layers? Because now across a filament itself, I have anisotropy, and then of course every time I hit an interface, there's again additional a break that is created at the interface between these two layers. So that is the issue. And the anisotropy, what we want to understand is the role of the interface. So basically this is a cartoon depiction of what is physically happening. You've seen this in yesterday's class. So you have one filament and a second filament that literally comes and sits on top of it. You have the fluid rich layer of the two filaments that are interacting. So what do you have now? If you have more paste there, and what is happening there, we really still don't understand. Is there some miscibility of the paste that's happening? Is there some ion transfer that's happening? Right? So what kind of mechanisms are active here? We still don't know, but essentially a bond develops there. Right? Some kind of a bond develops there. And maybe at some level, we can think of the mechanism as similar to what we would have when we go place fresh concrete against some old concrete, like a cold joint. Right? So you basically, how does a bond develop when you place fresh concrete against an old concrete? At some level, we expect that the cement paste from the fresh concrete perhaps penetrates into the porous structure of the old concrete, and that's where the bond is developing. So perhaps there is some chemical bonding that's happening, and there's also some physical bonding that may be happening where the paste from the new concrete penetrates into the pore structure. So, but at this point, we still don't completely understand what's happening at the interface, but an interface forms. What is the problem with the interface? You've already seen this, that because this fellow is not exactly compacted in any way, we are not vibrating it in any way, we are not agitating it, so it's a naturally formed interface, right? Or naturally, as in when with the two filaments simply resting against each other, you do get this interface which does allow a faster penetration of liquids, water. So you'll have seepage if you don't have a proper interface that's formed. Water will get in preferentially. More worrisome for me is that then chloride ions and all these other ions can also get into the concrete. So the filament itself may be very good, very strong, but the weakest link now becomes the interface, where everything will directly go right through the interface. Not just that, if I have a weak interface, that will determine the strength of the composite, isn't it? If I have a chain, what determines the strength of the chain? The strength of the weakest link. Now, what do I have here? I have a chain where I have multiple filaments that are connected by the interfaces. So if I was to pull on this, what would happen? If I pull on this, basically the strength of the weakest interface would determine the strength of the entire composite. Right? So these are the complications that we have to deal with when we're talking about the interfaces. And So fundamentally, how do we identify the interface? You'll always see these cartoons that we keep drawing, but that's the best guess. That's all we can say. I mean, if you actually have well bonded filaments, sometimes it's even very hard to pick out the interface. There's actually good interpenetration. That's what I think happens. But at some level, yes, if you have old concrete and new concrete, some kind of an interface does form, right? I've kind of shown it here with these two colors here. Now, what are the concerns here? What is the dimension of this interface? We still don't know. Is it millimeters? Well, yes, those are all the solutions. First, identify the problem. We'll so get into what, and I'll show you that these two work. Now, the question is, what is the dimension of the interface? Is it microns, micrometers, or is it millimeters, or what, or is it 1 millimeter, 2 millimeters? What is the physical dimension of this? We're still kind of grappling around with it. The other thing is what is physically happening or what is happening at the interface. When I dump one layer on top of the other, is there some interpenetration of the cement paste itself that's happening? Is there some ionic movement that's happening across the interface? Because remember, the concrete is fresh, it still has some dissolution of cement has happened. It's already rich in calcium and some of these ions. Is that happening? Right? So we still don't understand. So what is the origin of the bond between them? Irrespective, you can expect that when you place one layer on top of the other and you're simply relying on the weight of the other layer to kind of provide any kind of compaction, there will be air gaps that will be produced. And we do see that this interface is actually more porous than the bulk material. So now there are also other issues that come up. When we're printing layer, there's also time gap between the layers that come up. Now, if you look at time gaps, you can actually identify two different scales. One is a short time scale, the other is a long time scale. And within the short time scale, we can actually have a gap between the first layer and the second layer. That depends on the geometry and the speed with which the nozzle is moving. And that could vary on the order of a few seconds to a few hundred seconds. That's the typical time gap that you get. Then, I don't know if you were paying attention yesterday, the printer was being halted at several times, right? And that was while they were reloading the pump and the mixer and all these things. So there's also a gap that comes about this. The concrete is still fresh, right? But the gap perhaps is now a few minutes to tens of minutes. Concrete is still fresh, right? But this within the short time scale, this reloading basically is going to account for a time gap on the order of minutes. Then you get the long time scale. This is when you take a break, like what happened last night. They stopped printing and today they're going to continue. You get a cold joint. That concrete has basically set and is way past set that we printed yesterday. The new stuff is going to come and sit on it, right? And this is the same problem as what you would see when you place old concrete and new concrete, right? So we have different time scales. Now, what is the issue with these time scales? So if you look at this, this is basically actually quite an old data set, 2012, when they started printing. They realized that this gap matters. So what they did is they actually printed a few layers of this material, waited for some time, and then printed a few more layers. Then what they did is they cored through this and they took out cores, cutting across the old and the new, right? And then they tested these cores in direct tension. Okay. Now, when you test it in direct tension, what they're interested in is this interface that is formed between the old and the new. Now, this old and new, the time gap could be the short time gap or the long time gap. So I could actually print specimens continuously where I go for the time gap that comes about from the nozzle moving around or the contour lap time. Or I could basically, it could be the time gap that comes about from reloading, which is on the order of minutes. Or I could create cold joints where I deliberately wait for longer time and see what happens. This is what they saw. This is the direct tensile strength of the material. That is the material of the filament. Okay, so if you actually test, if you are able to test the filament itself in direct tension, this is the direct tensile strength of the filament itself. And you notice what happens here. The tensile strength essentially amounts to the bond strength, because when they tested it across this here, this is the weakest link between old and new, right? And that basically you see that it starts dropping. And the more you wait, the weaker the bond that is established between the older and the new. And what is worse is even when I have a zero time gap, now there's physically zero time gap is impossible. So what does zero time gap represent? It's a time that it takes to complete one lap. So I basically go one lap of the nozzle, come back, I'll print the next layer. So the zero time gap is the natural time gap that I get between the layers when I print out one loop, come to the next loop, right? So that is the zero here. So even the zero time gap is actually weaker than the strength of the filament. So by its very nature, the filament is weaker. And the more I wait, the weaker it gets. Of course, and you also notice something else, that is a large scatter, and this always creates a problem with printing as to what strength do I report, right? And whenever you have such large scatter, what would you report? The average? Is that good enough? Should I take the lowest? In which case there's no end to it. It could be lowest, could be zero, right? So that is always tricky. And the fact that you're all thinking makes me believe that we still don't have a solution to this, and we don't. Okay, because this becomes important for design. Why? Because when we design concrete structures, we take the characteristic strength. What is the characteristic strength? It's a 5 percentile value, right? What does that mean? I'm taking a 5% risk. There's a 5% probability that the concrete that I'm producing is weaker than what I'm prescribing. That is a 5 percentile value, right? Which also presumes that my standard deviation is within some limit. You can't just have random standard deviations, right? And what is the standard deviation we typically take? It's about 5 megapascal. That itself is quite high, right? Which means that you have some semblance of quality. But look at this. The scatter, if you look at it, is actually so large that it's almost on the range of the strength itself, if you look at it, right? So this creates a problem, and this is a problem when I start looking at trying to design with this material. Which strength should I take? Okay, so this is something that we really need to carry on in the back of our mind. And then you see what happens with the interface. So this is, you saw in the morning, you get this preferential penetration right through the interface. Why? Because we are not doing anything to help with the bonding there. I'm simply placing one filament on top of the other, right? And these are all active areas of research. Then what could I do potentially to improve that interface? How can I, reduce the preferential penetration through here? And if I do this simultaneously, I'll get increased bond strength. That will help with the mechanical properties, right? Why do you think we get such a large scatter here? Part of the reason has to do because when you're testing it, you're essentially testing the strength of the interface. And the interface itself is so variable, right? You're simply printing one layer, putting another layer on top of it, and the gaps between those layers are closing by themselves, and we are not making it homogeneous in any way. So that is the reason why you get such a huge scatter in these results. Okay, and this is the acknowledged reason that we have for this large scatter. Now, if you look at the printing process itself, this is exactly what was been done yesterday. You have a mixer, they dump it into a pump, it comes out of the nozzle. This is a process called direct deposition, where in the kind of printers that we are using, basically the material goes from a pump. This is what we call a progressive cavity pump, and it's pumped directly to the nozzle. Nozzle simply helps place it, right? So in a lot of other printers, you will see that there will be a compaction mechanism at the end. So the material is pumped, it goes into a compactor. It's usually an auger compactor. The material is compacted and extruded. Okay, so there are two kinds of printing systems that are available. What we did is that we actually printed with concrete, and the idea was to actually see what would be the admixture, what would be the impact of it, and more importantly, what we're interested in is fluidity. What would happen if I printed something that is more fluid, and if I printed something that is harder, as in it didn't have that much fluidity. Now, why are we interested in that? The reason we are interested with that is, remember that if I make concrete more fluid, what will happen? I gain because the pumping pressure goes down. Okay, I gain potentially because suppose I print a filament and I print the next filament, what happens? Now I have a fluid rich layer, fluid rich layer. So basically what will happen, the chance of forming a good bond is very high, because now I have fluid rich paste on the top of the first layer, fluid rich paste at the bottom of the next layer, and so fluid interaction, basically some mixity may happen and I may form better bond. That is the idea. But what do I lose? Shape retention, because it's more fluid, it will deform, right? So when I print something, I may expect a 50 mm filament width, I may end up with a 70 mm because it's much more fluid. So pluses and minuses. And whenever we're talking about printability, there is no fixed value. Please remember this. There's always a window in which you can print. right? So and there's always a trade-off between shape retention and these other benefits that you get from fluidity. So we tried the different fluidities of these concrete mixtures and we printed these specimens. And the reason I'm even showing you the specimens is recently there was a round robin test series conducted by Rylam where they identified the concrete scale. Now, what do they call a concrete scale? Whenever you place two filaments adjacent to each other, they're calling that the concrete scale. So if you basically only have one filament, they call that the mortar scale, and you print to the same concrete, but then if you're relying on the strength of multiple printed filaments adjacent to each other in the same layer, they call that the concrete scale. This is just definition semantics at this point of time, right? So we printed this concrete scale specimens and we reported our data into the database that has gone into this Rylam round robin test series. And from there, then we cut cubes and we cut the beams and did all kinds of tests with this just to see what would happen. Now, one thing interesting that I wanted to point out, suppose I start with the concrete with a certain slump. So this is basically concrete that went into this. AM1, AM2, AM3 are basically the concrete mixes that are printed with different doses of admixture, which is a super plasticizer. And you see that the slump actually increases. So basically this is AM3 is a much more fluid mix. Now, before and after pumping, when we did the drop table test, we find that the flow, as we measured it, right, the flow is impacted by the compaction process. So something is happening during the pumping and the printing. The material state actually changes. And you can see that here. Suppose I take AM1 and you look at the flow that I get from the drop table test before, that is a blue line, and after, you see there's a drop here. So there is, the material itself has changed during the compaction process. Something has happened where the material has gotten compacted or some change has happened. What happened, I still don't know. Now, let's look at the strengths that we get. So we did two kinds of strengths. One, we did split tension test. One where we tested across the interface. So you have two filaments. We put a small notch on both sides, put a hardened steel rod here, and did a split tension test. So when you actually put a hardened steel rod here and you press on it, what will happen? It will basically diametrically split between these two support points. So what we get is like a split tension strength, and you see the difference between the strength of the filament and the strength of the interface. This is with a zero time gap. What is zero time gap? Basically the time it takes to complete one circuit. And usually it's of the order of a few 10 seconds or so. That's it. Okay. So you see the difference here, right? So there itself, you have a huge difference between the filament strength, right, and the interface strength. The interface is not as strong as the the film. The interface is not nearly as strong as the interface. Then, of course, we did the compressive strengths. Three directions are identified. U is along the print direction. V is perpendicular to the print direction, as is W, right? W is such that I'm basically pressing the layers. If you think about the W direction, you have these layers printed in this direction and you're pressing the layers, right? V is basically perpendicular to the printed interfaces and U is along the print direction. These are the three directions that are identified. And so this also becomes important that whenever you're reporting strength properties of concrete, particularly extruded concrete, you have to identify the direction in which you're testing it. Okay, what do we see? Well, the strength in U, V, and W, they are in the reverse order, and you get a result that's expected. It is the strongest in the U direction, the direction in which you're extruding. Material is getting nicely compacted in that direction, right? And essentially, it's like fingers that have gotten extruded, and you're pressing on the fingers, right? So that gives you the highest strength. But needless to say, our standard deviation is still pretty high. And this is gotten from nearly, I think, 13 odd cubes that we were able to cut from the printed specimen. So it's not a small number. And so this number is not something that comes from just 3 cubes, right? Now, if you look at V and W, the weakest direction is V, when you're basically pressing it like compressing it perpendicular to the printed direction. So this is my printed direction. I have these fingers. If I test in this direction is where it's the strongest, right? And if I test it in this direction, where I'm basically pressing the layers, it is the second strongest direction. The third one is when I basically test it in this direction, where basically I'm testing perpendicular to the interface. That is my weakest direction. Now, one thing we can do, if we think like engineers, is that What if I said I treated this like a homogeneous material, isotropic homogeneous material, right? I pretend it's an isotropic homogeneous material and I give it a strength that I get from the weakest direction. And then I say this material is of this strength in all three directions, right? Seems fair, right? I mean, that's like an engineer's way of thinking where you say, fine, I have three directions and I select the weakest direction and then I determine the characteristic strength in this direction. What are the characteristics of strength? It'll be the average strength minus 1.65 times the standard deviation. Now, this is my average. This is the standard deviation. 1.65 times this happens to be conveniently around 30 megapascal. Okay, so for this concrete, can I pretend as if it is 30 megapascal concrete in all directions? Seems like a good way of thinking, isn't it? That's the engineer's way of doing it, where we say, fine, I know that I have three different strengths. I'll take the lowest strength in the weakest direction and pretend as if the concrete is the same strength in all directions. Right? So that's how we actually started. When we said, okay, when we have to do the design, let's do this. Right? Later on, I'll show you that that is not exactly the most best or the best way to do it. There are other things we need to consider. This engineer's way of thinking has to be refined. Okay. Now, the other things, of course, was that we also evaluated the anisotropy. We looked at the split tensile strength. So we are basically testing across the interface. So you look at this cube. This cube is being loaded in wedge splitting, where we are loading along the interface, basically. Now look at the strengths we are getting. Tensile strengths, horrendously low. Why horrendously low? Look at it, AM1, AM2, AM3, the stiffer concrete and the most fluid concrete. Well, good news is when I increase the fluidity, the split tensile strength increased, right? But look at the number here. It's barely 1.3 megapascal, right? What do we expect from strong concrete? Suppose I told you it's a 30 megapascal concrete. What tensile strength do you expect? Roughly, if I take it as 1/10 of the compressive strength, rule of thumb, right? That would be about 3 MPa. I barely have 1.3 MPa. Scary, right? So, two things. Even if I treat it as a 30 megapascal concrete, which from my engineer's hat, can I extend that rule of thumb, which says 7.5 square root FCK? Clearly not, because that number would give me something like 3.5 MPa or so. So one, if we need to extend our design principles the way we've learned it, we need to completely redefine the code. That 7.5 square root FCK has to go out of the window. We basically have to invent a new set of rules, because in tension, what's happening, the relationship between compression and tension is not following what we expect from cast concrete, right? So this is first thing that we noticed. Then the compressive strength testing, this is for different fluidities. You see that AM1, AM2, AM3 in the different directions of testing. Direction U, which is the strongest direction, V, which is the weakest direction, W, which is the intermediate. In all three of them, the compressive strength increased when we increased the fluidity of the paste that was extruded. Same thing with flexural testing. We get improvements there, but it's not so sensitive. We did chloride ingress as well. And what we find is, this is the which ponding test. So we did basically ponded these samples with chloride solution. So what happens when you pond chloride solution on there? Chloride ions diffuse through the material. What will happen? Basically, because I don't know if you can make out here, but you can see that right here, we had at the interface itself, we got preferential penetration happening right through the interface, right? So not only is the interface weak in tension, right, but it also allows preferential ingress of ions. Then we also did the RCMT test, and the same thing, you see, that we start getting this preferential treatment, preferential penetration that happens through the interface. And the preferential penetration through the interface starts decreasing when we increase the fluidity of the mix. So this is AM1, AM2, AM3. AM3 is the most fluid mix. You see, it's almost like the penetration itself has become quite uniform. So clearly, the interface, the way it forms, has an impact, will have an impact on the durability characteristics of this concrete. So that's another aspect of concrete that we use. So now, coming to the question, what can we do about it? So what was we said, okay, we have a weak interface. Let's see if we can functionalize the interface. Can we make it stronger? Can we make it less or more resistant to ion penetration? So we tried to spray between the layers. The idea is that you print one layer, immediately spray something on top of that, and see how that would help the interface, right? And conventional wisdom is that you try something like, where is the, my bonding agents. So these are the bonding agents that are commercially used, the styrene based and the acrylic based, which are used whenever you form a cold joint. So suppose in regular construction, you stop construction, and tomorrow if you have to pick it up, then what would you do? You'd basically put some bonding agent and then continue over, right? So these are commercially available bonding agents that are used. Now, the idea of the spray was very straightforward. Suppose I have the printing nozzle, I can put a spray head right behind it, so it'll continue spraying right behind it. And so when the next layer comes, the bonding agent is already there and it'll basically sit on top with the bonding agent in between, right? And we tried some unconventional things like carbon nanotubes, which we thought may help, and surprisingly, they did help quite a bit. Here's what happens when we, with the different spraying. This is my control with nothing. And for this, we selected the AM2, which is the intermediate fluidity. AM1 was a stiff concrete, AM2 was the intermediate, AM3 was the most fluid. So we selected AM2 and tried these different treatments, and you see immediately the split tensile strength jumps up to a value that you expect to see, right? You're getting close to 3 now, right? So yes, we can now start thinking about design procedures, provided I improve the interface. Okay, and that is the important thing. So here now I'm starting to get into the expected range of 7 to 12% of FCK. I'm starting to get there, right? And different treatments give different strengths, so that is something that we have to live with. Now, flexural strength, the same thing. So when you do the flexural strength, I expect to expected range is 0.7 times square root of CK. We start getting into that range with the different treatments. And look at the CNTs. They actually give very good performance for the interface. The same thing happened with the CNTs, the carbon nanotubes, sorry. Even here, see the improvement that you get. Of course, the bonding agents, the AC is one of the bonding agents, AB is one of the bonding agents here, the two extremes. They perform as we expect them to do. They improve the bond, right? Now, what else? Look at the chloride penetration. Here, a bar having a high value is not good. You want something that has a low value, low penetration. My control has a very high penetration. One of the commercial bonding agents didn't do much, but then when we got into CNTs and we started getting into the acrylic-based bonding agents, there was actually a nice drop in the penetration value. It's still nowhere near what you would get for cast concrete, but nevertheless a significant improvement. So now, what I want to talk about is, so going back, right? Would it be okay if I said I define compressive strength of this printed material in the V direction? Which was the V direction? Perpendicular to the layers, right? So U is along the print direction, strongest. When I press the layers, intermediate. Across the layers, the weakest, right? So would it be okay if I define my compressive strength in the V direction? Okay, take my tensile strength as 7% of root FCK, of course, with some kind of treatment, right? Flexural strength, maybe 0.7 of root FCK, again, with some treatment to the interface. And chloride penetration of the bulk material, we are almost getting there with some kind of a treatment. Is that acceptable if I was to design with it, right? Now, this is the key slide. If I have a general state of stress in a material, which is basically a biaxial state of stress, and we also have shear applied on it, how do we handle this? When we deal with concrete, concrete doesn't understand shear. Concrete only understands two things, compression and tension, right? So what do we do if I take a general state of stress? We convert it to principal stresses, right? And then we say, okay, now this is my principal state of stress. Concrete is going to crack across the tension, and I have to make sure that concrete can carry compression in the perpendicular direction. Wherever I expect to see a crack, if it's going to crack perpendicular to the tension, I'll put a tension reinforcement or introduce some kind of reinforcement to carry the tension. That's how I do my design, right? What happens when I have this bonded filament? Suppose I take the same stress state, okay? I transform it into principal directions. What do I see? This is my principal stress state. The transformation itself is independent of the material state, right? When you do the transformation doesn't know what material you're dealing with, right? It's just a transformation of stress. Now, what are you dealing with? Now, if you actually look at this here, right? you still create a condition of this form where your interface would still be subjected to some kind of shear. Okay, so the shear behavior of the interface becomes important. So the other thing is, my principal directions of the stress do not align with the interfaces. I cannot expect it to. Okay, so what is going to happen now? No matter whether I like it or not, these, because the principal directions don't align, the interfaces will be subjected to some kind of shear, either with shear with tension or shear with compression. Okay, and that would determine the stress response of this fellow. And so, just simply taking it as an isotropic material, treating it as an isotropic material with a strength which is the lowest that I derive from the V direction is not good enough. Why? Because if I was to continue loading this fellow in this stress state, in the biaxial stress state, the interface would actually see something like this, and it may very well fail in shear, which we haven't tested for. Right? So what that basically tells us is, if you want to get into this layered media, we really have to understand the shear behavior of the interface and go back to what we do with masonry. So, and luckily for us, before we jump into something mega complex like composite materials, we can borrow from what we were doing before, which is masonry. Right? Same thing happens even in masonry. What happens? We have layered interfaces. Right? Actually, masonry is much more complicated than your printed material because it has also vertical interfaces. It has horizontal interface and vertical interfaces. Luckily for us, it's mostly horizontal interfaces. So I can treat it as if it is a masonry with a super long brick. Right? So, but I can port whatever we learned from masonry in here. And there's some very nice, beautiful models that are developed from masonry, where fundamentally we do this shear test for a masonry, where you clamp the masonry. You basically a triplet test, 3 masonry blocks which are clamped together. I can basically apply different levels of compression by adjusting the tension on the tie rods. If I basically tension these tie rods that are going across to different levels, what will happen? The whole assembly gets different levels of compressive stress. Then when I push on the middle brick, what happens? The interface basically gets sheared. So I can get the shear response of the interface under different levels of compression. Okay. From there, I can draw a failure envelope for the interface. And what typically we find is that it follows like a Mohr Coulomb kind of a response. And where have you seen Mohr Coulomb responses? In some soil mechanics kind of a textbook or theory, right? So we can port all of that, what we already know, into analysis and design, provided we get the material properties. Now, what is the important property when you're dealing with masonry? You actually do a triplet test and you determine the shear strength of the mason or the mortar layer in the interface. Now, there are some nice fancy models that are available. We've done these tests because this is for masonry. We've done these tests for masonry, a shear test with different levels of compression. This is what happens when you have no confinement. When I apply a confinement of 0.2 megapascals, when I apply a confinement of 1.2 megapascals. So what is happening as I'm confining it more, the shear resistance increases. Right? So now, if I was to take the peak shear resistance from all of these 3 and plot them as a function of confinement, I would get a response that looks just like the Mohr Coulomb failure theory. Right? And essentially, that is what is used to develop the constitutive relationship of the interface for the case of the masonry. And one can get into really nice plasticity based formulations with fracture to understand the tensile response of these interfaces, like what is shown here. I will not get into the details. So this is all from masonry, understanding of masonry. And then we can, this is for masonry, but we can essentially extend the same thing. Suppose I have a masonry wallet. Now I can do a micro model. Micro models are available where the constitutive models of these horizontal and vertical lines, these horizontal and vertical lines represent the motor interfaces. And I can get the constitutive properties from the shear tests under confinement. Once I get that, I can calibrate the constitutive model and I can start doing predictions of things like this. This is for a masonry panel, right? We can do something similar for printed interfaces, where I can show you the cracks that would form across the interface. It is much simpler. What we are dealing with is simpler than regular masonry because of we don't have these vertical joints, right? So we can do all these fancy kind of things, which with existing tools that are already there, just port them to the case of our printed setups. And then we can start designing things like walls and all these things. Remember, this is from an analysis of what we call a masonry pier. What's a masonry pier? It's a wall made of masonry, which has some compression on top. So you see the compression on top, right? Which is subjected to the horizontal force. That means that this particular wall is designed to carry horizontal forces. Where would I see a horizontal force? When you have earthquake or wind, right? Wind would be more out of plane, and when you're talking about seismic, the significant resistance comes from the in-plane direction. So we can now start looking at this mechanics that can be ported from masonry and applied to the case of 3D printed assemblies, right? So here we have all the expertise with the masonry. Just simply apply it, right? And our problem, I believe, is going to be simpler than that of a masonry because we don't have the vertical joints. We only have horizontal joints. But we should be able to characterize those joints properly. What is the shear transfer ability of the joint? That is important, right? And in addition to, of course, the tension and the compressive strength, the tension properties of the interface and the compressive response of the aggregate. Okay, so can we still use like an engineer's judgment, take the weakest direction? Possibly, right? But then you always run the risk of not being able to identify shear induced failures. Okay, and a saner approach, something which is more systematic, would be something that we basically draw from our experience of masonry, brick or stone masonry. There are enough analysis programs that are available that you can analyze this at different levels of discretization. Whether you want to do a micro model, a meso model, all of those are available for masonry. Okay, so in my opinion, if we are really to get into the next scale, start designing, we really have to start paying attention to this, start characterizing the interface properly. When I say characterizing, I don't mean the microstructure characterization. I mean, how is it behaving under different stress states, right? And then we can calibrate a model like this. And as if you give me a 3D printed wall, I can give you the predicted response. Okay, right. That was the first part of my presentation. Now, the second part is where I want to stitch together this whole thing about sustainability, right? So why printing? Okay. And what is it that we're gaining with printing? And unless we address this issue of sustainability, we are not going anywhere. And the big talk of getting to net zero. What we imply by getting to net zero is zero carbon. Okay, net zero implies different things in different contexts. You could have net zero in energy, net zero in discharge. What we are looking at here is net zero in carbon. Now, big problem for cement industry because we've been tagged as the second or the third largest anthropogenic source of carbon. And just yesterday, I was talking to somebody about this carbon trading and all these things. So that is already happening. If that happens, cement, if we are to pay something called a carbon tax, will get killed. Our price of cement will double. Who's going to bear the brunt? Us. Now, why is it important in the India context? Our current production of cement is about 400 million tons today, right? 400 million tons. Our projected demand for cement by 2050 is 1.4 billion tons. 1.4 billion. That's a projection of just cement. And if you start tagging carbon on that, in India, we won't be able to build anything. It'll become too expensive, right? So, which means that we have to get to net zero. And there is serious thought being given to this. Our prime minister wanted us to become net zero by 2047. He said 100 years, let's do it. The cement industry looked at it and said, there's no way we'll make it in 100 years. They begged, they pleaded, and they've got this deadline extended to 2070. They said, well, at the earliest, we can make it by 2070. What are the different levers we are looking at? Well, if you look at cement, there are different things that are being considered. Now, if there are several ones like savings in cements and binders that will take us 9% of the way. What savings in binders? Well, I start reducing my clinker factor in cement by using fly ash, slag, and all of that. Savings in clinker production itself. I optimize the process. I basically try to reduce the energy consumption in the kiln and all of these things. That will take me probably around 11% of the way. But then there is this fellow, efficiency in design and construction, that if you actually pay attention to it, will take us 22% of the way there. What do we mean by that? Well, if you look at regular construction, this is what we have. Typical concrete construction, right? Two things come out of it. One, it is slow. I have to erect the staging, the formwork, tie my reinforcement, pour it, slow process. And oftentimes we call this a form cycle. How fast can you build one on top of the other with regular construction, right? And form cycles, if you can, now of course we are starting to crash everything and start, I've even heard of 3-day slab cycles, right? But that is a rarity, that doesn't happen. Typically more often we see like 28-day, 56-day slab cycles. So that is a big problem. The other biggest problem is this rectilinear form, right? What do I mean by that? If you look around, all the beams that you see are rectangular. Do they have to be rectangular? What am I losing if I make it rectangular? Sorry? I'm using more concrete. Why? If you think about it, let's come up with something called a material efficiency factor. Okay? How do you define that? You define some performance measure of the structure, say strength, capacity, or say stiffness. Okay? And divided by the weight. Okay? The worst form you would find is a rectangle. How can I improve the efficiency? Well, first thing is, do I need it to have a uniform cross section? I can take away material from the web part of it, create an I-beam, and that we know is structurally much, much more efficient. It'll give you the same stiffness, almost similar stiffness, right? And almost similar capacity, right? For much less use of material. Now, what is that extra material doing that is sitting in the rectangular beam? Two things. One, it's adding to weight, right? So what is the consequence of this? Well, let's go back to our RC design. Now, when I suppose task you with designing a 10-meter beam, what would you do? You'd go back, you'd basically start with a certain rectangular size. You'd say, let the beam be 250 millimeters wide, let the beam be half a meter deep. You'll start designing it. Very soon you realize that that's not adequate, right? Even if you max out your steel that's allowed by the code, you will not have enough capacity. So then what do? Your intuitive thought is to go to a next bigger cross section. That's the most intuitive thing that we would do. What happens then? You've added more weight. Now what is happening? You basically start going down what is called a downward spiral. Now what's a downward spiral? Well, in order to support its weight, you need more material, and the material only adds more demand. Okay. Now at some point what happens is, if you follow the negative spiral, you can't even design an RC beam. And usually that break-even point is around 10 to 12 meters. You'll find that around 10 to 12 meters, if you start exceeding that, right, try designing an RC beam. You'll get stuck in that negative spiral. You'll not be able to design. And that is the reason why once we start getting longer in spans, what do? We go to pre-stressing. You can't design it otherwise. RC beams just won't survive. Why? Because you get caught in that negative spiral web, right? So what happens in the negative spiral web? Basically, the structure is working harder to support itself, its own weight, right? How can I alleviate this? Well, I can alleviate it if I can start printing structures like this, right? What is different about this? You take away material wherever it is not required, right? So what is the advantage I'm gaining in this process? The advantage I'm gaining in this process is I'm now working on the positive spiral, not the negative spiral, right? And here what I would say is, look, if you want to go longer in span, take away material, don't add material to it. Okay, it may seem very counterintuitive, right? But then what am I doing? I'm basically reducing the demand that I get from the dead load itself, the self weight. Okay, a very counterintuitive design proposition. And that's what we need to work on if we are going to make 3D concrete printing successful. If I'm going to still stick to these rectilinear forms, it's a lost proposition. If you're still going to print rectangular structures by 3D printing, it's a waste. You've not achieved anything. Because one, when it comes to rectangular construction, the traditional construction has already cornered everything. They have perfected everything. You're not going to beat them in the game, right? Two, I'm basically working against my own weight. Why would I want to do that when I can actually take advantage of the shape forming process that I have and create shapes that are structurally efficient? So There is basically, if you look at this whole effort of sustainability, I can break it into three scales. One is the cement scale, the second is the concrete scale, the third is the structure scale, right? If you look at predominant effort in sustainability, everybody talks about this. You go to any conference, 90% of the papers will be focused on this. So they'll be looking at cement. And you'll see 90% of the paper, they'll be talking about binary, ternary. Now I'm starting to see quaternary blends, where they're blending this, that, and whole lot nonsense, and then trying to create cements. What is the objective there? You want to basically reduce your clinker factor, the cement that you're adding in there, right? And why? Because cement is the one that is tagged with the big carbon footprint. So that's what you're trying to do. Scale one, that is the clinker, right? The cement scale. The second scale is the concrete scale. This again has gotten less attention, but perhaps we could squeeze a little bit out there too. How? Well, that's yes, but that is, but from a sustainability point of view, from a cement carbon footprint point of view, what could I do here? Supplementary cementitious materials are this. Huh? Mixed design. What did we do in mixed design? How can I reduce my cement? Larger aggregate, better packing. If I really pay attention to that, what happens? My paste requirement goes down. What is paste made up of? Cement, isn't it? So I can actually start making concretes more efficiently. I basically use better packed aggregate, actually pay attention to the packing, right? And I start using larger sized aggregate to start with. That would help me with this. And there are a whole bunch of other tricks too that people are resorting to. But then this is my scale too. I get some savings there. This is a scale that we haven't really looked at so far. Very few people have paid attention to it. Now it goes by different names. People call it as lean construction, right? And only the architects are pushing this whole lean construction without understanding a damn thing about lean construction, right? The other thing is, what can I actually do with this? Where can I optimize this on the structure scale? The whole point is, suppose I ask you to design a structure conventionally. You come to me with the design saying that, sir, this is what you told me. Here is your structure, right? Now, I tell you, I'm going to produce the same structure at a fraction of the cost, a fraction of the material weight, right? And that is the structural scale where we look at structural design optimization. How can we do this? Well, we'll have to start looking at structural shapes, start using some of these concepts where instead of going with rectilinear shapes, we try to optimize on the shapes, right? Come up with efficient structural systems, which basically give me better performance with lesser use of material, right? This scale is what we're talking about here, this one. So, and this should give us about 22% savings in carbon. Okay, and what we're going to do is actually look at this. I'll skip this. So in extrusion based 3D printing, let's see how we can actually implement this. And this is one thing that I did want to point out. Now, Professor Surya did mention this, but we do have an ASTM standard that's available. Those of you who are serious about printing, get hold of this ASTM standard. It explains the whole process of solid modeling, tessellation, slicing, and everything that is basically standardized in the industry. And what you saw yesterday in the field, basically all of these process, this is what is followed even in concrete 3D printing, right? And a little bit of a background. 3D printing is a very well-established field. We are not new to it. Bioprinting now is a big craze. A lot of, they're even talking about tissue printing. In fact, at IIT Hyderabad, we have a whole biomechanics group that is looking at printing skins, which are used for skin grafting and all these things, tissues. So these are all happening already. What is the difference with what we are doing? Scale. They talk about millimeter to centimeters. Our starting point is a meter, isn't it? So we have to do what they do, scale it up. And often that's where things break down. A lot of times when we do printing, it's very nice. When you do a laboratory toy scale printer, it works beautifully. You take it up, scale it up, the whole thing just falls apart. So that is something that you have to prepare yourself for with printing here. This is a nice video, but let's see if we can quickly play this. This is not mine, but this is clay printing by these CNC robotics. But you see the kind of shapes that you can do when you actually have good control of the material. This is all clay that is being printed, right? The kind of definitions you can start creating. And look at this. It's not even cantilevering. They're cantilevering from here. right? And look at the stresses on the interface here. What would you see? This thing essentially would just slide off if you don't print properly. That means the interface, the shear strength of the wet interface becomes very, very important. But we can do these things if you actually engineer your material. Um, yeah, and just quickly run through this. This was actually the structure that was 3D printed almost 7, 8 years ago. This is open for the World Fair that you see here. This is a house that is printed by Perry. One of the actually, their Perry is a formwork company. They own formwork, and this you've already seen. This they've already extended this to organic shapes, and this is done with clay, compressed clay, Adobe. So it's a nice livable surface that has been created in Italy. A whole bunch of things. This is in India. This is done by Twasta, in fact, and I'll later on tell you some of the advantages we get with this shape that has been created. But the whole point here is that if you were to look at these, all these, none of the shapes are purely rectangular. You take advantage of the geometry, a dome-like structure where material is naturally in compression, right? And again, here you don't see really rectangular shapes, right? So you're taking advantage of the freedom that you get with the shapes. And now let's actually build on this. And of course, this is the structures that you saw yesterday. And you can extend this. This is the temple that was shown to you yesterday. I think today we'll have a video on this. But this is the Modak shaped mandapam that is there for Vinayaka. This is the mandapam from the inside. And then this is the world's, what we claim is the world's first 3D printed temple that is not too far from here. Right? Slabs also? No, no. So slabs are conventionally cast. Okay. In fact, actually, let's look at this. It's actually a very clever construction. So you see these columns here, these are conventional columns. Okay. So, and inside there, you see the printed structures, and the domes are 3D printed. Okay. So it's a clever mix of both. Okay. And that brings me to a very interesting subject, which is, suppose I was to look at a structure like this and for design. Now, this is not perhaps the structural element that you're seeing here, right? The structure is probably hidden inside there. So what does that mean? This is a shell which is housing the structure inside. What kind of a structure would you conceive? Beams and columns, right? Now, today what we're doing is we print these structures, leave spaces inside for columns, and do conventional beams and columns. The reason is we've not yet come to the point where we trust this printed form enough to be load carrying. So what do? We opt for redundancy. It is that this fellow can carry load, but I'm not going to trust it. So I will embed a reinforced structural system inside it. So when I'm printing it, I will leave pockets where I want beams and columns. I'll introduce conventional reinforcement for regular concrete. Of course, there's a lot of redundancy, but the thing is, at this point, because we don't have enough data or design guidance on this, we're resorting to that. Okay. Now, one of the clever uses of printing is this. Now, when I have printed elements and they're off-site printed, right? How can I bring continuity between these elements? One of the quickest ways to do it is by post-tensioning it. And this is something that is done in Netherlands, where they basically printed this segment. So this is basically like a bridge, where different segments had different shapes, right? And basically they were strung along by PT. So basically continuity between the elements was brought about by post-tensioning. A nice, neat idea, because tension is carried by the PT cables, and these printed elements go into compression. And you know that concrete is strong in compression. So you're basically separating out compression from tension. Let the concrete carry the compression. Steel in the form of PT carries tension. That steel is also providing continuity. It also basically allows you to marry all these elements together, create one big structure. So we could think of clever applications like this, where basically the printed form, let it take compression and let there be a separate tension path. So yeah, I'll skip all of this. Yes, a few things I wanted to mention. Pumping itself, right, is not new to concrete. We were able to pump concrete to a height of 600 meters when Burj Khalifa was built. So we have pumps that can pump concrete any height that you want. So what is it that is different in the pump that is doing for 3D printing? What is the different expectation? When we can print half a kilometer in the sky, why are we getting stuck with 3D printing? The requirement must be different, isn't it? What is that requirement that is different then? We're talking concrete here, right? But why don't I use this pump? And sorry? Well, yes, maybe I can control that vibration. The issue is volume. See, this fellow can throw gallons and gallons of concrete in the air in no time, right? This fellow. What do I want? Precise flow. And that precision is where a lot of these pumps are lacking. Throwing a bulk quantity in there is no problem. We can do it. What I need is that precision pump. And that's where we are getting stuck, is the precise control of the volume of flow. And so we had to take a few steps back. It's not that we didn't have concrete pumps. We have pumps that can pump concrete to 2.5 to a height of half a kilometer in the sky. But that precision control is what made us take a few steps back. Okay, and that's where we're getting stuck. The toothpaste analogy, I know you've heard of it yesterday. Okay, now we expect our toothpaste to flow under pressure, comes out of a nozzle, keeps its shape. Right? All of us have our preferences, but the toothpaste I like the best is the one that keeps its shape beautifully coming out of the thing. I don't want something that becomes a goopy mess like this on my brush, right? And it's a highly engineered fluid. What probably you don't realize is 95% in the toothpaste is just fillers. Only 5% is what goes into cleaning. That's it. The remaining 95% is just fillers. The fillers are packed in there, which give the paste the rheology control. And there are some world-class rheologists who work for companies like Colgate-Palmolive, helping design toothpaste, right? That is, they help you design the 95% that goes into the toothpaste. The 5% part, the chemists don't get paid that much in designing a toothpaste, right? Now, you probably have seen this if you haven't, right? We talk about extrusion, right? If you look at extrusion process is also not new. If you look at the forming of this hollow core slabs, if you've ever seen it, the way it's done is they dump concrete onto this. It's a slip former. As it's moving along, it extrudes. I don't know if you can make out here. It extrudes a hollow core slab with these openings. Okay, so the concrete comes out with the openings and it keeps its shape. Okay, so we already knew this, and this is like 30-year-old technology, 40-year-old technology. So what has changed? So why is it there's a big show about printing then? Well, this is consistent. I mean, precast elements. And here I'm able to use larger aggregate. I'm not limited to what we're doing with 3D printing. Sorry? Look at the boxes. I am able to hit shape retention, but this fellow is not pumpable. What do? They literally dump the concrete into the hopper and they literally squeeze it through the extruder and it comes out with this shape. Okay, so I only tick one of the three boxes. The other two still remain open. Okay, so we are able to, I showed you that we've mastered two boxes, right? I showed you that I'm able to pump concrete. I was able to send concrete half a kilometer in the sky, and shape retention is right here. This is the way it is extruded. But the issue is with all the existing technology, we were able to tick one of these two boxes, but not both simultaneously. But now we've added a third box, which is this fellow. Now try doing this by adding more layers on top of this. That is printing for you. Okay. And that is where it gets very, very complicated. So we really had to take a whole bunch of steps back and say, yes, I have mastered this, but wait a minute, I need controlled flow. I mastered this in this, right? But I need to tick the other two boxes as well. So which means let me go back, re-engineer the material, re-engineer the system, and then start printing. That's where it becomes very, very complicated. It's not that extrusion is difficult. We've done it before. It's not that pumping is difficult. We've done it before, even more significantly than what we've done. And this whole thixotropy then comes into play with buildability, right? I've already illustrated this to you. I'll skip. So this is the other thing that you get this instability when you're printing. Some of you are printing and probably notice this, that everything is going well up to a certain point. Of course, there's some cracks here. And without any notice, and you see the groans on the back, right? So without any notice, suddenly it'll go, right? So it's not just about shape, the buildability, but also the stability of the printed layers while the material is still fresh. Okay, so that also has to be considered in the design itself. That's also, and we are not used to it because the concrete is still fresh. Whenever we talk design, we talk hardened concrete. So that means we have to bring in design concepts into the fresh stage also. And you had a whole lecture on, 2 lectures on this yesterday. So only when we answer all of these questions do we get into something that basically gives me, when I handle thixotropy, I get something with a low enough viscosity, high yield stress. Am I able to produce a mixture that is pumpable, is basically printable? And what comes under printability? It is pumpable, it is extrudable, and it also has shape retention. Okay. Now, if we do this, and we go to the next step. Now I want to bring in, talk a little bit about shape optimization and what is form optimization. I'll just illustrate this with a video, right? And I did talk about this yesterday. So this is just a flat piece of paper. Can't carry any weight, right? Now, the minute I make it into an arch, suddenly it starts carrying more load. What has changed? This is the shape of the structure. But even that has a limit. Just notice the next shape. See this, right? It's not corrugated, right? It's what we call the diamond in or diamond out. Impressive, isn't it? What has changed here? It's the shape. So why not take advantage of this? Why should I still stick with a flat surface? Now you understand why we had those dimples on the printed structures. That is our trade secret. It will carry much, much more load than a flat surface. Okay, and this brings us into this whole concept of shape optimization. I'll quickly run through some slides on the bridge and what we did with the bridge. You've already seen this. So the idea was that we exploit this concept and start with the concept of a tied arch. So we said, let's build on this concept of form optimization, where we keep concrete compression separate from tension. Right? You need to have both, otherwise you'll not have equilibrium. If one material is carrying compression, you need a tension to balance it, otherwise you'll not have equilibrium. So we said we'll go with a tied arch. This is literally a sketch from my notebook as we were discussing this. This was actually a project for an MTech. A few MTech students got in. You saw the video. They were all students who worked on this, and we delivered on the bridge. This is the arch in concrete, which will be in compression. This is a tie. So now it's like a bow, right? What happens when you place load on it? The concrete goes into compression, right? If you don't tie it, what will happen? It will simply kick out, right? If you just leave the arch here, what will happen? Put load on it, it will simply open up, right? So to hold it in place, you need this tension tie. That's why this is called a tied arch. So we said this is how initially the first, the shot of the bridge was basically this tied arch. But the problem is, if I give you a bridge like this, the riding surface becomes curved. Now it's like climbing a mountain and coming down. That's not exactly friendly. So then we said, okay, let's exploit this feature further. Go with a beam. So if you look at a beam and you subject it to a UDL, what you'd see is that the top part of it goes into compression, and these darker shades here, reddish and the orange shades, are tension. Bottom is essentially all in tension. So why do I need this? Concrete in tension is anyway useless. So suppose I take this tension part away, I end up with a shape like this. Have I lost anything? Nothing. Basically, I've removed this, which contributes to weight, right? And I'm putting a tension tie here. Don't forget the tension tie. So what do I get? I get a compression form where concrete is in compression, which is held together with this tension tie here. Right? Can we do any better? Well, we can. Actually, what you can do, or what we can do, is something that follows along the lines of topology optimization. Except when you do topology optimization, what you do is it becomes a mathematical exercise. You say, fine, you determine the final shape outcome of this structure such that given these performance criteria, but deflection, strength, capacity, what have you. But then what happens is you have no control on the shapes that come out. You may get filaments of different widths located in some random location. A mathematical exercise. What is the problem we have? Our filaments are more or less confined to be of the same width. So we thought that we follow a slightly different process, and we'll try to basically, if you look at this compression form, put a truss inside there. Okay, develop a lattice kind of a structure inside this compression form. And then we optimize the lattice structure such that we can minimize these members. Remember, each of these members that you're seeing here is a printed filament. Okay, now we minimize this, and going through the process, I'll quickly show you the minimization process that happens. So this is what we started with. Look at, these are all the filaments. This is a two-part bridge, part one, part two. This is the closure pore. These are all the printed filaments. So we basically optimize this and end up with this. So what you see on the field is this optimized structure, where we basically iteratively placed, varied the spacing of the filaments, the number of filaments, such that I do not compromise on the capacity. So we are looking at the capacity and do not compromise on the stiffness of the bridge, the deflection of the bridge. These are the two controlling criteria. Now, how are both possible? Well, as I'm removing, if you look at the member density here is much higher, member density is much lower here. So what happens then? The weight of this structure is much smaller compared to this. So why is it that I'm still able to get the same capacity? Remember that when you're talking about capacity, what is the capacity catering to? The weights, of which self-weight itself is a big significant component, right? So when I'm reducing the number of elements, what's happening? And the capacity has to match the demand. So what am I doing? Positive spiral. I'm reducing my demand, and so the capacity requirement goes down. Okay, this is the upward spiral I'm talking about. So I did not compromise the capacity. Yes, if you were to check the absolute capacity, yes, these may be different. But I don't need this much capacity, because essentially a big chunk of the capacity goes into supporting its own weight. So when I started removing elements, what happened? The weight became less, right? And I needed less material to support it. Okay, so that is the beauty of this upward spiral, the positive spiral, right? And that's through the process that we came out with this final shape, which then we printed, and we also put some steel elements in there. I'll quickly skip through this. The idea was to see if we actually put some steel between printed layers, can it take some tension? And the idea, if suppose I print a layer, simply put a steel wire between the two layers. And when it cracks, will the steel wire take any tension? So for that, we did a fracture test with this. And this is what you get for plain concrete. Basically, it goes up, it cracks here, a crack opens up and falls apart. But the minute I put even a simple 3 mm wire, you see that it basically now it's able to retain some stress. Not much. Remember, this is just smooth wire. There's nothing holding it. We just put the wire between two layers. That's it. That's all we've done. But there is some residual resistance that's coming in. How significant is this resistance? We can actually, let me show you, I'll skip the fracture part. So this is the response of the bridge. I don't know why this is not coming up. Sorry. So this is the response of the bridge that we analyzed just to understand how it would fail. Now, initially at this point 1 is where small tension cracking happens on the top filament. Okay, then more and more cracking happens as it builds up to 0.3. So what is happening from 0.1 to 0.3? More elements are getting cracked. But what happens? Remember that little bit of residual stress that's available when you put a wire filament there? Because of that, what happens is the load redistribution that happens within the bridge, and eventually failure happens in compression. When the compression strut, the bottom arch which is in compression, when that fails in compression, the bridge fails. And that only happens at this very high load. I'm sorry that you're not able to see the X and Y. But when we actually predicted the capacity, what we found is that even for this bridge, the capacity that we had was almost 5 times of what was required. So that we could have still done more optimization for the requirement of the bridge, right? So which means that I could have still saved some more material. Now, and I'll just show you the video here just to show you printing in real time. It's very fast. And you saw this yesterday, the same printer, right? So now, if you go by this speed, the time gap between one layer and the second layer is going to be a few seconds, 10 seconds, 12 seconds. That's what it is, right? And that's how we came up with this bridge. Now, what we found roughly is that compared to conventional design, this bridge was half the weight, roughly half the weight. If I gave you a design exercise and say, look, you have 7.5 meters that you have to span, and you have to provide me 1.2 meter riding surface. If you go about designing it, you would have to design a one-way slab. You do the design of the one-way slab, you'd see that with this bridge, we have basically achieved a 50% weight saving, right? Now, the question is that good enough? Now, why do I even say that? Well, two things are happening. I'm saving material on the structure scale. That's a positive, right? How much material? 50% material, right? But is it good enough? What is the problem? Cement content in the concrete. The one that I'm printing with anywhere from 800 to 1000 kgs per cubic meter. Regular concrete, conventional concrete should be 350 to 400. Double or 2.5 times the amount of cement, right? So now we are starting to do the sustainability analysis, the LCA analysis, as we call it. And two things. The LCA analysis shows us that at best we break even. Why? Because I've saved 50% of the material, but I'm using double the cement. And where is the carbon tag coming from? Primarily from cement. So what's happening? I'm halving one, but doubling the other. So essentially, I'm just catching up. So at this point of time, even with this impressive number, this bridge is just about breaking even. So what can I do to make it more sustainable? You have to address that big problem of cement content. So unless we are addressing that, right, this technology will not truly be sustainable. That is, if you use carbon as your benchmark, as your tag for evaluation, right? Now, we've done that analysis also, and we are finding that if we get to something like, let's say, 600 kgs per cubic meter, so you drop it from 800, 900 kgs per cubic meter to 600, then you have tremendous savings in the carbon tag. Okay, and this number, in our opinion, can still be improved. Half is not good enough. I think we can go further, where we can have 70% material savings. Okay, bottom line, I'm not using rectilinear shapes. Please remember this. If you still are stuck to rectilinear shapes, you're not saving anything. So form, structural form, which is not rectilinear, form optimization or structural optimization, and material. If you play with all three of them, you'll basically hit all three boxes. Cement, the binder, the concrete, and the structure scale. You can actually hit all three of them, and essentially you're looking at potential carbon savings of up to about 50%. That is the kind of savings you can have on a regular structure. Okay. Now, some of you, whenever I project this, they'll ask you, but how do I extend this to a house? Be creative is my answer. So these are the numbers of sustainability, but I just wanted to show you, you have already seen this, but I wanted to show you that this is the what we did with the on-site printing. Oh, I'm sorry, I stole this video from you. Just to show you that we can actually get into automated construction nearly. So this is the site that was given to us. Getting to the site itself was a challenge in itself. And this is, mind you, at 14,000 feet. The same robot that you saw, same robotic arm that you saw yesterday, the trials that were done. And then finally, we were able to get a mix that was printing without cracks. And the development of the material mix itself took some time, so that to prevent it from cracking, get the curing, everything done properly. Oxygen content is so low, the efficiency of the machine drops significantly. So it was operating at 50% efficiency. Remember, this runs on energy of some form. And finally, look at the shape here. It's not flat for a reason. Okay. So again, it's form optimized, right? You remember the crinkled paper, which is much better than a flat paper, isn't it? So we can actually push the envelope with this kind of printing. And now we are taking it to the next step with taking form optimization to further. Why? Suppose I have to print something which is like an underground tunnel. We can actually do that in this form. Why do I do a box culvert that is rectangular? Okay, we've actually form optimized it, borrowed from the eggshell. So now we're starting to print these eggshell shaped structures. Where what is beautiful about eggshell is that it is a beauty of nature. It can carry tremendous amount of compression. If you actually press down on an eggshell, it takes a lot of force to break it. And if you look at the thinness of that shell, it's hardly anything. It's a beauty designed by nature, right? So why not copy that shape into our tunnels, right? And that's what we are doing in for the subterranean bunkers, okay? And we are looking at underpasses, which can be printed in eggshell shape. And these are form optimized, right? And so I can now give you a structure which has tremendous capacity in compression. I'm using the material where it is the strongest. This really doesn't even need any reinforcement because everything goes into compression, right? So I can now start talking about underpasses. I can start, we are looking at airport hangars. For defense applications, now we are looking at protective bunkers for our soldiers. Of course, then we'll have to get into the concept of UHPC, which is a concrete which is much, much stronger than our regular concrete, much tougher or has a much higher energy absorption. So with that, then we could start printing the structural shapes that are very, very resilient and taking advantage of geometry. Again, so come back to the shape again. Why is this shape so beautiful? It basically is perfectly in compression, a dome. And we see our temples that were built millennia, not just centuries, millennia ago are still standing because they took advantage of this geometry. A dome is beautifully in compression, right? You use the material where it is the strongest. Why did we stop doing it? We grew impatient. It takes time to grow a dome, right? It takes skilled labor, which we don't have anymore. So what did we do? We opted for flat shapes, which are not very efficient, right? So here now is basically a call for going back to what we were doing previously, what we were doing right, and adopting it for 3D printing. Now, this particular structure is actually a structure built in Bangalore by Twasta. The crinkled skin that you see is a functionalized skin for this gives you very high temperature performance, very good temperature performance. So thermal conduction through these walls with this crinkled skin is actually very, very low. So this constructed facility is nice and cool. Yeah, now how can I take it to the next level if I really want to be very sustainable? Start printing with geopolymers. Now my starting point is fly ash or slag, right? And I'm only using sodium hydroxide, sodium silicate. At some level, there is going to be a lower carbon tag. One of the biggest problems with cement is the intrinsic carbon. What is intrinsic carbon? You have to burn calcium carbonate to produce calcium oxide that you need for making cement, the calcium silicates. Now, that you can't get away from. But in geopolymers, the intrinsic carbon is essentially zero because I'm starting with a waste material. Now, of course, this is not a legitimate solution for everybody. Your starter point, we have plenty of it. India, we are still burning coal and we get plenty of fly ash. So for us, this is potentially a great material. If I can start printing with this, my net carbon tag would be very, very small for the structure, right? And that we believe is going to be the future. So in summary, so if you want to get to net zero, even with the current cement-rich mixes, we have, through form optimization, we have savings in the carbon, right? And we are doing so without compromising on the performance. Whatever bridge I demonstrated had the required capacity and the stiffness, okay? Now, when we are designing structures like bridges, often it is stiffness that matters more than the strength. You don't want to stand on a bridge where you feel the vibrations, okay? And oftentimes the member sizes are dictated by stiffness more than the strength, okay? We found that our bridge was actually very, very stiff. Most of you were standing there. Did any of you feel any vibration there? And you would have actually stood even on staircases. Some of the staircases, if you jump on the staircase, you feel the vibrations, right? So that is basically a serviceability issue. So we are able to match the structural performance requirement in our design. And we can basically have further improvements in carbon if you're tagging ourselves to carbon. by looking at its optimization process a little bit closer and trying to shave more material and look at reducing the cement content in our concrete mixes that we're printing. Last few slides where I present to you, currently there are no standards for printing, but this is the closest we've gotten to a standard. The ICC has put out a standard for 3D automated construction for 3D concrete walls. Okay, it's available. You can download it. You can look at it for guidance when it comes to structural use of this as walls. The problem there is that they really don't give you anything in the form of an equation that will help you design anything, because they're fully aware that the same concrete that is printed using your printer or mine will be very different. What they do is they guide you, saying that, look, you can follow this process. And with that, then you can look at designing of these walls. Okay. Then we are not to be left behind. So we are also taking up the standardization of 3D concrete printing in BIS. It's being unfortunately being taken up by CED 32, which is the committee that deals with precast, prefabricated structures. They're bringing it out as an annexure to IS 15916. That this is a guideline for 3D printed concrete structures. This is currently in the discussion stage. I think it will come out public this thing shortly. But again, this document also doesn't give you a whole bunch of things that will help you design anything. It basically lays down the guidelines of what we consider as printed concrete and how you can potentially use this 3D printed concrete in structural applications. Now, here is what this code is, this particular draft is very good at. They say, if you don't, well, two things. One is this is use common sense, use established mechanics, and then go about designing. What established mechanics? Well, I already laid the case for you. Like what we did, am I justified in saying my compressive strength of 30 MPa is good enough for designing the concrete structure? The compressive strength in the weakest direction? Yes and no. You take a call. Okay. And that's what this code is also saying. The second thing it says, if all else fails, build a structure, test it to failure, then you know. How many of you would be willing to do that? Well, the reason is because it's called design by test. And all but few very large companies like say L&T would be able to do such an exercise. So while data is still incoming, while we are still assimilating all the data from all over the world, I think they're not stopping you from building structures with 3D printing. They're saying, well, use your common sense, okay? And at the end of the day, you justify that you have adequate capacity, or you design something, even a prototype, or build something that's a prototype, load test it to failure, use that as a feedback for your design process. That's also allowed. Okay. So with that, I'd like to conclude my presentation. I think I've stuck to time, 12:30. So thank you for your attention. I think we've gone a full circle. So we've gone a full circle where we've started with rheology, linked up everything, ended up with structures, right? And I think I'd be very happy if at the end of the course I've had you question the very basics. Maybe if you thought you knew it before you came to the course and you're more confused now, I'm a happy person. So, but the point is that to open up all this information to you and make you think about all of these things, it's an open field. A lot of things that can be done, a lot of missing information. And as each of one of us does these things, and we start contributing information into the global pool of information, then from there, eventually guidelines will come up. This technology will come to a point where we'll start using it with confidence. And that we are still in that process where different people around the world are basically using this, and we are pumping out data into all our journals and all these things. At some point, I think we'll have enough data that we'll be able to design with confidence with all of these things. All these structural concepts would have matured, right? But that would mean that the design itself would have to see a paradigm shift, where now we cannot just say, okay, I give you a compressive strength of concrete, 0.7 square root of CK is your tensile strength. Maybe that won't work, right? Maybe we'll have to look at it differently, right? So that is yet away, I think, but the rapid pace at which we are progressing, I'm quite optimistic that in the next few years, we'll start seeing serious attempts at developing codes for use of this technology, codes for designing structures that are fabricated with this technology, and actually seeing some large-scale structures come into being. Right now, what we see are a lot of boutique structures. I think at some point, we'll start seeing some serious structures enter the market. Okay. So with that, I think I'll take a break. Let me invite Hanuman to make a brief presentation, the one that he could not make yesterday. So I know I've stolen a lot of his thunder.